All right, I'm just going to go ahead and rework example 7a so that you can pick up kind of where we left off. Mr. Korpi, that's me. He's taping ends down to a 12-inch diameter LP log. This is a true story, by the way. I don't know if the video yesterday said that, but I got bored a lot at the house, and we had these big giant fire ants outside. I think this was in Laredo, Texas. So I would just tape them down to the turntable and watch them puke formic acid afterwards. So the formula that we're going to use here is V equals R. Is that W?
No. Omega.
It's omega. Very good. Y'all were listening yesterday. V equals R omega. So what we could say here is that the ant's linear velocity is directly proportional to its radius. The farther away it is from the center, the faster it has to move to make one rotation because the circumference is larger. Okay, so angular velocity in this case is going to be the same. This W omega, right? This is going to be a constant in this problem. The record is spinning at a constant rate of 78 revolutions per minute. That's called your angular velocity. That's omega. So if you want to call that omega, there you go. So that doesn't change, but the linear velocity changes based upon how far they are from the center. So for 1 inch, we're going to say V equals 1, and I'll include the units here, 1 inch times. Now, let's do this one time off to the side. 78 revolutions per minute. I'm going to write it like this, revolutions per 1 minute. I want to convert that to, we want the velocity in feet per minute. Okay, so the minutes are good. The time unit is good. But I need to convert revolutions to what? Nope. Whenever we're talking about rotation, we have to convert our measure of rotations to a very specific unitless measure. Radians, right. So we can measure rotation in rotations, revolutions, laps, degrees, whatever. But those are all specific units. So I'm going to convert this once off to the side. 1 revolution is how many rads?
2.
No, close. No, that's worse. 2 pi. 2 pi. 1 rotation is 2 pi. 1 revolution or 1 rotation is 2 pi radians. Everyone agree? That's once all the way around. Okay, your revolutions are going to divide out. So what's 78 times 2? 156 pi. I'm going to leave it like that. Rads per minute. This is the omega that we're going to use in all of these calculations. Okay, so I plug that in over here. 1 inch times 156 pi rads per minute. Now let's see what the units are going to be. That's going to give you inches rads per minute. What's inches times rads per minute? Inches, very good. This gives you inches per minute. Very good. Gives you inches per minute. What do we want to measure our linear velocity in? Feet per minute. Ay caramba. So I can't stop there. I need to convert inches now, so I'll do it again in the problem. This is dimensional analysis. I want inches to divide out, because it's really inches over 1. And then I want feet to appear. So what's the conversion there? 12 over 1 or 1 over 12 or something different? 1 over 12. Okay. So now I know the inches divide out, and my resulting units are feet per minute. And rads is just the description. This is why dimensional analysis is so important. You really don't even need formulas. If you can multiply or divide things from each other so that the units work out to be what you want, the formulas kind of take care of themselves. The dimensional analysis guarantees you get the right answer. All right, now I'm going to go to the calculator. Minnesota. I think Minnesota's going to get Kirk Cousins back next year. I don't think they're going to trade him. Yeah. He got the Aaron Rodgers injury this year. He's a nice guy. He's a nice guy. If you've ever talked to him in person, I haven't. But I've seen people talk to him in person. Yeah. Those are called interviews. Yeah. All right, let's go ahead and do we want to leave pi visible or just multiply it in? Let's multiply it in because we're talking about feet per minute. We want to get something that we can appreciate. So 156 pi. Do we need to worry about times 1 divided by 1? Do we need to worry about times 1 divided by 1? No, it's the identity element of multiplication. So I'll just put divided by 12, and we get to 3 decimals, round or truncate? I'm a big truncator. 8, 4. Do we need the 0 then if we truncate? Really? I mean, come on, it's a 0. Do we need it? Absolutely, we need it. Yeah. All right. So that's going to be feet per minute. Feet per minute. Hey, you want to convert it to miles per hour? We can do that after the fact. This answers the question, feet per minute. Now, if you're going to convert it from miles to hour, I wouldn't write feet per minute with the slash right there. I would write it like this: feet per 1 minute. That's how I would write it. So let's go ahead and convert that to miles per hour. We're going to need to convert minutes to hours, so let's do that first. It doesn't really matter. What's the conversion here? 60 to 1 or 1 to 60? 60 to 1. The minutes divide out. We're left with hours. Okay, that's our time unit that we want. And now we need to convert from feet to miles. So feet go on the bottom, miles go on the top. And now everyone has to know this conversion factor. I'm not going to give it to you for this short test. What is it? 5280 miles in a foot? 5280 feet in a mile. 5280 feet in a mile. 5280 feet in a mile. Natsu, I'd give it to you because y'all don't use feet in Japan, right? Y'all use meters. What do y'all use for distance? Okay, so you use the metric system. Yeah. So you don't know there's 5280 feet in a mile. You know there's 1,000 meters in a kilometer. I'd give that to you. Yeah. Now everyone else needs to know it. Okay. It wouldn't be bad if you did memorize that, Natsu. Yeah. And then you can go back to Japan and say you're Americanized. You know there's 5280 feet in a mile, and you know the Super Bowl. Right. Yeah. You don't even think in terms of feet. Like you have no idea. Like how tall are you? Cent- Centimeters. Right. Yeah. Not 5 feet. Right. Yeah. We here in America, we have a keen appreciation for miles per hour because we drive automobiles and we look out for police officers and they will give you a ticket and fine you money if you exceed a certain speed limit in miles per hour. So we have a keen appreciation for miles per hour. All right, let's go ahead and take our answer. Do I just type in 40.840 or do I use the calculator stored version? Right. You never, ever, ever, ever use an approximated answer for a subsequent calculation. So 40.840 times 60 divided by 5280. So you're saying on the video yesterday I would have asked that question and no one would have replied? Uh, Losers. Okay, so 464 mph. We stylize it even. We don't even put mil divided by h, right? We stylize it mph, miles per hour. That's a little less than half a mile per hour. Is that ant moving very fast? No, not really. Not really. Now, what if I move that unfortunate ant out two more inches from the center, and now he's at 3 inches? Well, it's still going to be V equals R omega. Let's write that formula every time. The radius is now 3 inches, and our angular velocity that we're using is still 156 pi rads per minute. All right, you want to go straight to miles per hour here? Just like say, forget the instructions of feet per minute. Let's go mph. Okay, we'll do that right from the beginning. So for 3 inches, I need to convert inches to miles. Do I go straight from inches to miles?
No.
I don't know how many inches are in a mile, but I do know there's 12 inches in 1 foot. So now the inches divide out, and now I know there's 5280 feet in a mile. So now the feet divide out, and we have our desired units of miles. Now I just got to convert from minutes, because rads are unitless. I got to convert from minutes to hours. So minutes on the bottom, minutes go on the top. 60 minutes is 1 hour. Minutes divide out. And now you kind of take inventory. What are the units that we have left that haven't divided out? We have rads miles per hour. What's another name for rads miles per hour? Just miles per hour. Yeah. So I know we have the right setup. So now we just type everything in except the ones. 3 times 156 pi divided by 12 divided by 5280 times 60. I just go from left to right. You can do all in the top and then divide it by all in the bottom, whatever you want to do. As long as if it's in the bottom, you're dividing, and in the top, you're multiplying. So you hit enter, and you get 1.392 mph. He's going a little faster. He's going a little faster. Now, they're both spinning at the same rate, aren't they? They're both spinning at 78 RPM, so they both have the same what velocity? Angular velocity. They both have the same angular velocity. They're both spinning at 78 RPMs, but they have a different linear velocity. The one that's further from the center is moving faster because
the radius is bigger.
yeah, so he's got a longer distance to travel, right? In the same amount of time, he's got to go a larger circumference than the one that's closer. If you've ever been on a merry-go-round, you've kind of experienced this for yourself. Now, y'all are probably of an age where you didn't even have merry-go-rounds at recess, huh? On the playground, there were no merry-go-rounds. But back when I was growing up, not only did they have merry-go-rounds, they had gravel instead of soft mulch or whatever to land in. And you would spin that merry-go-round as fast as possible. One big guy would spin it, and everyone else would be white-knuckling and holding on to the very, very ends. And they'd fly off sometimes, and they would skid across the gravel into like broken glass and into like a telephone pole that was the edge of the and your dad and I used to do it all the time. Your dad and I have fond memories. There used to be one at St. Peter and Paul, and we would skip CCD and we'd go play on the merry-go-round. You can ask him about it. Yeah, yeah, yeah. Um, all right. Just for the record, if you're listening at home, that was a Seth Weber, and his dad is Jason Weber, my cousin, which makes Seth Weber also my cousin. Yeah. Yeah. Huh? No, probably third cousin.
Something like that.
Something like that. Yeah. No. But we text each other. Yeah. No, I quit going to big family gatherings a long time ago. But yeah, good times back in the day. 6 inches. He's further out from the middle, right? How much further out from the middle is he from 3 inches? Yeah, so do I have to set this whole thing up again just to get the answer? No. What number is going to change in this whole setup if I were to go to 6 inches instead of 3 inches? The 3. It would be a 6, wouldn't it? And so if I just multiply my final answer of 1.392 times 2, would that work? Yeah. In fact, I could have done that to get part B. I could have just multiplied my 1 inch times 3 to get 1.392. But it was worth doing the stoichiometry again. All right. So let's go ahead and do that. Oh, I typed in natural log, so I can't just hit times. I have to delete it and then hit second negative. Second negative brings up the answer from the previous line, times 2. And for 6 inches, we know the linear velocity. I'm going to go ahead and write with a highlighter and just pretend like I meant to do that. 784. I'm going to truncate. 2.784, and what are the units? MPH. 2.784 MPH. Okay? So this dude is almost trucking it at 3 miles per hour. The merry-go-round at St. Peter and Paul was the one I really got hurt on because it did literally have gravel around the base, and there was broken glass in there, and there was a giant telephone pole that had splinters on it.
Did you go to St. Peter Paul?
I did for a little while, yeah. And then I wanted to play football, so I transferred. His dad and I both went to middle school together, but we went to St. Peter and Paul in 6th grade.
I went to St. Peter Paul, and I used to play Foursquare a lot.
Oh, we played Foursquare a lot. Yeah, it was not much to do at St. Peter and Paul,
Yeah.
especially when they got rid of the merry-go-rounds.
They redid the playground, though.
Yeah, they did.
It's
Yeah,
not brand new. I was
yeah,
like, padded.
yeah. It's padded now. Yeah, back in the day, they didn't care.
Yeah, they had like a wooden playground back in the day, and there was like beehives everywhere.
Oh yeah. Absolutely, it was splinters galore. And just that loose gravel with broken glass. That's all I remember. It's like you better not fly off that merry-go-round. But that was the fun of it, right? No one wanted to like stay on the merry-go-round. It was like push us harder, push us faster. We want to spin faster so that we fly off, right? We fly off. All right. Any questions on example 7? Hey, and that's why I'm getting EEGs these days because I hit my head so many times flying off of merry-go-rounds. Concussion after concussion after concussion. Take care of yourself when you're young, right? All right, example 8. Mrs. Lincoln, y'all know Mrs. Lincoln, right? Right next door? Her vehicle has wheels that are 36 inches in diameter. Yeah, Miss Lincoln rolls on 36s, y'all. If she's cruising through Landa Park in her vehicle at the posted safe speed limit of 20 miles per hour, and I've had many speeding tickets in Landa Park over my lifetime, how many revolutions per minute are they making? Okay, so just an FYI, this makes a fantastic multiple choice question on the test. A fantastic multiple choice question on the test. All right, we're not going to do this by formula. I'm going to teach you how to do this entirely by stoichiometry. Okay? Stoichiometry. What value in here should we start with? Well, which of these two numbers that were given is a variable and which one is fixed, a constant? 20 is a variable because that's the one she has control over, right? She can slow down or she can speed up, but it's really a lot harder to change the diameter of her wheels. Yes, yes? So let's start with the 20 miles per hour. I'm going to write it as 20 miles per 1 hour, okay, instead of mph. Through some series of transformations by multiplying by uh, conversions that are equivalent to 1, we want to end up with revolutions per minute. Okay, I want to end up with revolutions per minute. So I need to get from hours to minutes, and I need to get from miles to revolutions. Would you agree? All right, which of those two is probably going to be easier? Let's do hours to minutes first. I think that's going to be easier. I want hours to divide out, so I'll put it in the top. I want minutes to appear, so I'll put it in the bottom. And of course, everyone but Natsu knows this. Y'all use hours and minutes in Japan, right? Yeah, okay. There's not a metric version of that. All right, so 1 hour is 60 minutes. Carry over from the ancient Babylonians, the sexagesimal system. All right, hours divide out. Now I need to get from, oh no, that's it, right? We got our time. That's it. So now I need to get from miles to revolutions. Well, here's what we need to do first. We're measuring her tire in what units? Inches. So I need to first get from miles to inches. That's my strategy. So let's go ahead and get from miles to inches. So I go miles on the bottom. And do I again know how many inches in a mile? No, I have to go through the middleman of what? Feet. So 5280 feet. I'll give that to Natsu, but no one else in 1 mile. The miles divide out. And now I can get from feet, I'll put feet in the bottom, and I get inches in the top, and 12 inches is 1 foot. Now the feet divide out. So what are my current units that I have? Inches per minute. Is that what I want to get to? No. Okay. So the next conversion factor is the magical conversion factor. This is the one that's going to get us from a distance to a rotation. Okay. I want to put inches down here, and I want to put revolutions up here. 1 revolution is how many inches? What quantity do we call that? Perimeter. What's the name of the perimeter for a circle? Circumference. The roundest of all Sir Arthur's knights. Circumference. 1 revolution is the circumference. What's the formula for circumference? 2 pi r or pi d, right? 2 pi r or pi d because 2r is d. All right, so how do we find the circumference if we know the radius? Do we know the radius? Ah, it's not 36, is it? 36 is the diameter, so the radius is 18. So let's go ahead and plug that in there. It's 2 times pi times 18. That's the magical conversion factor. That's how you get from a linear distance of inches to rotational distance, okay? It's the circumference. 1 revolution is the circumference. All right, so now the inches divide out. Sure, that's fine. That's what 18 times 2 is. What are we left with now in our units? In the top we have revolutions, and in the bottom we have minutes. If you memorize circumference as pi d, by all means, you don't have to take half of the diameter just to double it in the calculations. Most people remember it as 2 pi r. It works either way. All right? Now, here's the thing that most students screw up with. They don't divide by the right quantities. If it's a factor in the bottom, we're going to divide by it. If it's a factor in the top, we're going to multiply by it. You got it? So all I got to do now is go from left to right, top to bottom. I don't need to worry about all the ones, do I? Because anything times 1 or divided by 1 is itself. So here we go. We're going to do 20 divided by 60 times 5280 times 12. And now here's where students screw up. I have to divide by, here's what they do. They divide by 2 pi like that. Is that correct? No. What that's going to do, you either put 2 pi in parentheses, because that's going to divide by 2 and multiply by pi, or you could just say divided by 2, divided by pi, and divided by 18. They each get their own divided by symbol. or you put the whole thing in parentheses, 36 pi. Okay? I think it's easier just to divide by each of them separately. That's super important because guess what? On the test, you're going to have an answer choice that's going to be there if you actually type it in as 2 pi instead of 2 divided by pi, and you're going to think you're getting the right answer, but actually the joke's on you. You got the wrong answer. Yeah. I did divide by 60. That was the second number I put in. Yeah, you can do it. You can do this one of two ways. You can either type in all the numerator, times, and then come back and sweep the denominator, divided by. I just kind of go from left to right and take care of all the factors. But you do want to make sure you get them all in there. All right, so at the end, this is 186.741. I like to truncate. And then, of course, we stylize revolutions per minute as well as RPMs. Your automobile has a tachometer in it probably that measures engine rotation, and it's your RPMs. Okay, usually times 1,000. Is this a reasonable number?
Yeah.
186 full rotations in a minute? That's not reasonable?
Yeah.
That's like 3 per second? Is that reasonable?
Yeah.
1, 2, 3. Yeah, it's a reasonable number. 3 rotations per second about? Yeah. Going 20 miles per hour? Yeah, yeah.
A lot more.
That makes you appreciate how fast them wheels spinning if you're going 70 miles per hour, right? You want to be an ant taped to that. Yeah, you're an ant taped to that. You better, you're dead. It's like you're flying off the merry-go-round. So you probably had a rock stuck in the tread of your tire at some point, and as you're driving 20 miles per hour, it's still hanging in there. Like, oh crap, the angular velocity is increasing. So is my tangential velocity, right? Because in this formula right here, or whatever, in this formula here, the radius of the tire stays the same, and it's your omega that's increasing. As you drive faster, your tires spin faster, and so your linear velocity increases. We call linear velocity also tangential velocity. You know why we call it tangential velocity? When you have a circle like this, the tangent line is the line that comes through and kisses the graph at a single point. It glances off of it. If you're spinning faster and faster and faster, there might be a speed, an angular velocity at which you're spinning so fast, you fly off. And you always fly off in the direction of the tangent line. And you always fly off with a linear velocity that's equivalent to your linear velocity as you're spinning. Okay, that was me flying off the Ferris wheel, or the roundabout. What do we call it? The merry-go-round. Yeah. This is also the tire. If you drive fast enough, you might hear something hit the bottom of your wheel well. And you're like, what was that? That was the little rock that was stuck in your tire tread coming loose with tangential velocity and hitting the bottom of your wheel well. Okay? Happens to me all the time because I got a gravel driveway part of the way. Tangent. This would be like if a spaceship was orbiting the Earth and it started orbiting too fast, it would fly off and break the orbit and fly off in a tangential velocity. What if the moon started spinning around the Earth faster and faster and faster, and it flew out of orbit? It would fly out of orbit on a tangent line right there. The surfers would be mad, wouldn't they? Yeah, because now we don't have waves. Hold on to your homework, everybody. This is back when we had paper homework. The iPads are heavy enough they might not fly off. Do y'all feel the air current right now? No one's hair is blowing. What if you put your hands up like this? Oh, you got the fan over there. Do y'all feel the air current going by? Like when you're driving down the highway in a car and you roll down the window and you stick your hand out, it pushes your hand back, right? And sometimes you leave it out there like, this is relaxing. And the car behind you is like, are they waving at me? What's going on? And you're like, I don't care about the car behind me, man. I'm just living my life. We're traveling through space right now at incredible speeds, and we don't even feel it, do we? It's amazing. Let's figure out how fast we're going through space right now. Approximate the linear speed of the Earth in its orbit about the sun. Assume that the orbit of the Earth about the sun is nearly a circle. It's actually an ellipse, but it's a pretty round ellipse whose average radius is 93 million miles. How far away is the sun on average from Earth? 93 million miles. You think it's exactly 93 million miles, or it might be 93 million point oh oh one, right? To be exact, right? It's approximately 93 million miles away. So let's go ahead and draw a little scenario here. The orbit of the Earth is there, and we got the sun in the middle. There's the sun right there in the middle. It's yellow. And then we got Earth right here. Earth, we'll call it E. We'll call this one S for sun. The radius right here is 93 million miles. We want to know how fast this thing is spinning. So we want to know basically if Earth were to break out of its orbit and fly on the tangential velocity, I want to know what that tangential velocity is. Hopefully Earth does not break out of its orbit around the sun, right? We would all get cold and there's not enough coats to go around. So let's go ahead and plug in what we know. The linear velocity is, what's the radius of the Earth from the sun? 93 million miles. I don't know what that is in kilometers, Natsu, but it's more than 93 million. Yeah. I'm going to put that over 1. Now I'm going to multiply by the angular velocity of the Earth around the sun. What's the angular velocity of the Earth around the sun? It makes one full rotation every 365. If we want to be more accurate about it, yeah, 0.25, baby. Happy leap year, everybody. It sure the heck is. Sucks if you hate February, right? It's actually 365.25 something, something, something. It's not exactly 0.25, but 0.25 is good enough. 93 million miles, and that's going to give us what units do we have now if we were to just multiply that out? Miles rotation per day. Is that what we want? No, there's two things we need to do. First of all, let's focus on rotations. I don't want rotations in there. I want to measure rotations in a unitless measure called a what? Radians. So rotations need to go. So from high to low, it's in the bottom. And rads need to appear in the top. One rotation is how many radians? 2 pi. Very good. So now we took care of rotations. So now our units are miles per day. We want to get it into miles per hour because that's what we appreciate most. So I want days to divide out. Do we know how many hours in a day? 24 hours in one day. So now days divide out. And let's see. Let's take inventory of our units. I have miles per hour. Is that what we want? Sure, let's do that. So we'll just go to the calculator now, and we'll type that all in. 93, 93 million, divided by 365.25, times 2 times pi, divided by 24. You can type it all in one line. All right, big bucks, no whammies, all right? Holy mackerel! 66,659.392 miles per hour. What? How did I do it wrong? What do I need in parentheses? No, I just multiplied by it twice. It's in the numerator. Remember, if it's in the denominator, I divide by 2 and I divide by pi. If it's in the numerator, you can put it in parentheses, but you're going to get the same result because it's in the numerator. All right? So it never really was funny to the police officers when they pulled me over for going 50 miles per hour in a 20. And I was like, well, officer, if you take the rotation of the Earth into account, we're all speeding through Landa Park. I was just going a little bit faster, 66,600 and or 709 miles per hour instead of 79. And he's like, shut up or I'll break your tail light, right? And fine you for that. Right. It was one night my wife lived at the very top of Landa Park on California Street. She wasn't my wife then, but we were dating, and I had to get her home by midnight every night. So I was always kind of like really close to midnight. Like I'd try to get her home at 11:59, to try and maximize the time with her. So there was one time I was coming and I turned off of where the KC Hall is on Seguin Street or whatever it is, Landa Street. And I was cruising, and the Officer Ives was tucked into that little entrance right there by the golf course, by the mini golf course, about the worst entrance. he was tucked in there surreptitiously, and it was like 11:58. And I was like, I got plenty of time, and I'm cruising there, and I know that I've gotten tickets in Atlanta Park before. I'm not an idiot, but I was going 35, and I was slowing down. I promise, I swear, I was slowing down, approaching 20 miles per hour. But he caught me right there when I was still going 35, and I said, Officer Ives, I got to get her home in the next 30 seconds, or I'm going to meet his sawed-off shotgun, her dad's sawed-off shotgun. And he's like, well, you're going to have to do this first. And I thought he would let me go, but no, he didn't let me go. I got another. That was the last ticket I got in Landa Park. And then I got in trouble for getting her home late. It was a horrible evening. So now every time I pass that spot in Landa Park and she's with me, I'm just like, hey, babe, remember that night? And she's like, yes, yes, I do. Yeah, it was good. See, it makes memories. Uh, in Landa Park, like 4. But I got 5 tickets in 2 years. My wife was at UT, and once at Baylor and once at UT, and I was at A&M. And I would go see her every weekend. I would either drive to Waco when she was there or to Austin from College Station. And I got like 5 speeding tickets in 2 years just trying to go see her. And they were big tickets. Like I'm talking like that was back when the speed limit was 55, and I was going like 85, 90 in a 55. Let's just say I paid a lot of money. I took a lot of defensive driving, and there's something called deferred adjudication, which I exercise my right to do that. I don't speed anymore. I don't speed anymore. I've learned my lesson. I've learned my lesson. I've had, um, they almost threatened to throw me in jail one time. I was coming home from San Antonio at the IMAX Theater, and right there in Selma, they caught me. They caught me going 85 again in a 55. And supposedly, if it's over 30 miles per hour over the speed limit, you're supposed to go to jail. And he could have clocked me at 86, which would have been 31 miles per hour over the speed limit. But I think he rounded down to 85. He was a truncator, not a rounder. Thank God. So I only got a hefty ticket. And I had to go, instead of paying the ticket to lower the ticket, I had to go see the judge with my dad. That was embarrassing. I had to go do community service in Selma. So for like 3 months, I would get dropped off at Selma every Saturday morning. And I'd have to go pick up trash in the park, and I had to work in the dog kennels, which I didn't mind that, but I had to do community service just to get my ticket lowered. It was kind of so. Don't speed, guys. It's not worth it. It's not worth it. We're already speeding, right? We're already going. Do y'all feel that? We're going 66,000 miles right now through space. But wait, that's not it, because this is a ride like no other. Because as we're going about the sun, what's happening with what else is happening? The Earth is spinning, right? So as we're going around the sun, the Earth is spinning. So if you've ever, one of my favorite carnival rides is called the Sizzler. They used to have it at the Comal County Fair. Your dad would know. And it was a ride just like this. You were on this big arm, and the big arm was circling around this big radius, but the cars at the end of each arm themselves were also spinning. And if you timed it just right, you could feel the concentrated G forces of both of the spins. And you got pinned up against the side of the thing, and you'd always have the little guy sit on the outside, so you'd crush him. And he was like, I didn't know this was the ride. And you're just like, shut up. And you're crushing him. We're on a ride like that. As we're going around the sun, the Earth is spinning on its axis. Y'all want to know how fast we're spinning on our axis? Let's figure it out. If the radius of the Earth is about 3,960 miles, again, the Earth is not perfectly round. The Earth is a spheroid. But if we assume that the average radius is 3,960, roughly 4,000 miles, that's good to be culturally literate. What's the linear velocity of a math student who's sitting in his math class in Ecuador, which is right there at 3,960? Well, V equals R omega again. What's the radius of the Earth? 3,960 miles times what's the angular velocity of Earth around its own orbit? It makes one rotation every what? 24 hours. Yeah. What are our units right now if we just multiply it out? No. Miles rotation per hour. Do we measure speed in miles rotation per hour? No. You try to pull that off with the police officer, and he's going to break your tail light and fine you more money. We need a unitless measure of rotation. We call that the what? The radians. So I put the rotations in the bottom. I get the radians to appear. One rotation is 2 pi rads. Now the rotations divide out. And now what are our resulting units? We get miles radians per hour. But what's miles radians per hour also known as? Miles per hour. Is that what we want? Yeah. So we always check the units before we do the actual calculations. Now, let's go ahead and do the calculations. 3960 divided by 24 times 2 times pi. I get 1036.725 mph. Holy moly. You mean to tell me that we're flying through space on this automobile at 66,000 miles per hour, and while that's happening, we're spinning at over 1,000 miles per hour? What I mean by the concentrated effect, if you hit it right here, let's say it's spinning counterclockwise, if you hit it right here and we're going around the sun like this, you get the 66,000 plus the 1,000 added to it. But if you feel it on the backside here, it's 66,000 minus the 1,000. Right. You can, and that's what makes it such a good ride, because you feel the oscillating effects of those G forces. Okay. So this is fun to remember for the rest of your life. We're going through space at roughly 67,000 miles per hour, or you can say 66 if it's easy to remember. 666, the number of the beast. Oh my gosh. We're going through space at roughly 66,000 miles per hour. And while we're doing that, we're spinning roughly at how many miles per hour? 1,000, right? That makes it easy to remember. That's fun knowledge to share with your grandkids. Hey, grandkids, do you feel that? Stick your arms out. Do you feel that? We're spinning at 66,000 miles while we're spinning at 1,000 miles per hour. Grandpa, you hit your head too many times.
Last promise. I don't think we have enough time. Mr. Korpi,
Hey,
do you think that, like, say you're hunting or whatever,
okay,
you're taking a shot at a mile,
right.
would you have to counter in,
The Coriolis effect,
yeah,
which is the spinning of the Earth?
yeah,
Yes,
at a mile you do?
probably so. Now, it's probably going to be just very small, like a centimeter, if that, but you would have to take that into effect.
What about like 10 miles?
Yeah. At 10 miles, yeah. At 10 miles, definitely. You could actually do the math, right? You can ask any sniper that they take into account the rotation of the Earth. They call it the Coriolis effect.
Can you snipe someone for 10 miles?
I can't.
No, I know, but like,
Can it be done?
yeah.
We'll have to ask the sniper.
You make a great video about that.
That would, right?
10 miles.
You got to take in the wind. You got to take in elevation, because remember, as you shoot, the bullet is falling to Earth at 9.8 meters per second every second. Right? That's gravity. Yeah. So there's a lot. You got to aim high. You got to aim into the wind, and you got to aim into the rotation of the Earth. And then the bullet will land on its target, which is just a target. It's not a person. Right. We only assassinate wooden targets in this class, okay?
Yeah.
Wooden targets. All right. So here's the deal that I'll make with you. We'll stop right here for today, and that means the homework is not due tomorrow. We will finish example 10 tomorrow relatively easily, and I will give you the rest of class tomorrow to work on your homework, which will be due Monday morning. And then we're going to quiz on Monday over linear velocity and angular velocity and area of a sector and all that stuff, okay? All right. So quiz Monday, homework due Monday. Any comments or questions? All right, cool.